Today, class, we're going to talk about the area inside of a polar curve. So we have this curve here. We're going to say, I'm just going to say in the first quadrant, but it's r equals f of theta, which I'll just refer to as r of theta. So the first thing is you partition off your curve like so. And we're going to imagine a slice here. Okay, so this is the ith slice. Okay, so what we do is we pick a theta I in the interval. Okay, so we're just going to pick some theta here, and we're going to look at r of theta I. Okay, so the thing we need to do before that is what we're looking at here is we're going to approximate this with just one arc of a circle based on that r of theta I. So that's going to be the radius of that circle. So the area of a sector, how do you calculate that? Well, you do the area of the whole circle and then you just divide by or multiply by what fraction of the circle you have. So this would be pi r squared, and then you're going to multiply that by theta over 2 pi. So that would be, so theta would be whatever angle you're using, and that would be how much of the whole circle you have. So that simplifies, notice, down to 1/2 r squared theta. Okay, so if I look at this ith slice, okay, and I'm going to try to draw it slightly irregular. Okay, so if I'm picking my r of theta to be this right here, basically I'm approximating the area of that little piece by the area of the circle whose radius is r of theta I. So the area of the ith slice is going to be, well, it's going to be 1/2 r of theta I, and I should say this is not equal to, but approximately equal to. And then it's going to be whatever thetas I'm using here in the interval, so this would be delta theta. Okay, so this would be the area of that slice, and then if I take the sum of all those and change it into integral, I get that the area is going to end up being 1/2 the integral from a to b of r of theta squared. I forgot to square it up here. So r of theta squared d theta. So that's my formula for the area under the or inside of a polar curve. Okay, so before I do an example, let me just draw another couple of pictures here. So when I'm thinking of a polar curve, I'm thinking of traversing it this way. So this is how d theta is supposed to work, and this is how dr is supposed to work. R is supposed to go from, when you're looking at your function, you're going from, not from the bottom up, but you're going from the origin out. Kind of very different, not like. In rectangular coordinates, you're thinking this way. So when you're thinking dx, you're thinking left to right, and when you're thinking dy, you're thinking bottom to top. But with once again, with the polar curve, we're thinking theta is going radially out, and so not theta, r is going radially out from the origin, and theta is going counterclockwise as an angle spins. Okay, so I'm going to do an example for you. We're going to find the area inside of a circle, which we kind of already know what the answer is going to be. So we're going to find the area inside of r equals cosine theta. Whoops. Cosine theta. So we already know what that's going to be. So if we remember correctly, when I'm plotting that curve, it's cosine, so it's centered on the x-axis. The a value is 1, so the diameter is 1, so the radius is 1/2. Okay, so it would start here and go this way from theta equals 0 around. Okay, the thing we need to understand as well is that this circle gets graphed on the interval from 0 to pi. Okay, so pi is back here. R would be -1, which really places me back over here. So I would start when r equals 0. When theta equals 0, I'm at 1, so that's where cosine is, so I'm out here. And so that's the deal. So we already know what this area is going to be. That's the area of a circle whose radius is 1/2. So the area is going to be pi times 1/2 squared, so that's going to be pi over 4. So we know what to expect for our answer. Okay, let's just make the calculus work for us. Okay, so we're integrating. We've figured out the angles are 0 and pi. So we're integrating from 0 to pi, and we have a 1/2 on the outside, and it's cosine theta squared d theta. Okay, so this is where the fun stuff happens. So what we need here is we need a trig identity. So if you remember cosine of 2 theta, this is 2 cosine squared theta minus 1. Let me move that over. So if I solve that for cosine squared, I get cosine squared theta is 1 plus cosine of 2 theta over 2. Okay, and let me go ahead while we're here. I'll tell you the one for sine, because you're going to end up needing that one too. So sine squared theta is 1 minus cosine of 2 theta over 2, and you derive it in the same way. You use the double angle formula for cosine, and you use the one that involves sine. So it'd be 1 minus sine, 2 sine squared. Okay, so back over here. So we're going to change this into 1/2 integral from 0 to pi of 1 plus cosine 2 theta over 2 d theta. Okay, and this is where the fun comes in. So I'm going to split this integral up, and this is going to be 1/4 integral from 0 to pi of 1 d theta, okay, plus 1/4 the integral from 0 to pi of cosine of 2 theta. Now with trig integrals, this happens an awful lot. So you need to be looking for it, you need to be aware of it, and you need to know when you're seeing it and what to do. So if we remember the period of cosine of 2 theta, so how do we find that? We do 2 pi over b, where 2 is b. So that's 2 pi over 2, which is pi. So if we look at this, we notice that's one whole interval. So what does that mean? Well, cosine is a periodic function, and if I were to graph it, just like sine, if I were to graph it, I see that there's equal area above the x-axis and below the x-axis. So what that tells me is that integral is 0. So all I really need to do is calculate this integral. So the integral of 1 is theta, and that's just going to end up with a pi there, so pi minus 0. So this is going to be 1/4 pi minus 0, which is 1/4 pi, which is what we expected.